Yeah. Yeah. All right. Yeah, we're back, and it's game 100 or 2005. Sorry, and today we're talking about and it's the fall 2017 semester, of course, and it's officially week 8. That's from. I'm going to count it as week 8. How about that? Right? And we can go from there. So even though it says section 6, it's actually week 8. In our schedule, we have quite a few left. I'm not sure if anyone has a chance to take a look at the website. I'm not sure if this is even broadcasting properly. You could be seeing some weird stuff, but hopefully you'll see what I'm seeing. All right. Yeah, you're good. So, laws of motion. Why are they important? Well, because they talk about mostly, I think the thing you want to focus on is it's all around forces and mass. You have a mass of an object. You're going to apply a force, which is energy, to an object, and it's going to react to that energy that you're transferring somehow. Okay, and energy can be in the form of different things. Passive energy, like as an example, the energy from gravity. Gravity is kind of active, but there could be other things that we can't do. So there's this guy, Sir Isaac Newton. I mean, if you haven't heard of him yet, you heard of him today with this funky picture, right? He really thought about mechanics, right? The idea of motion in 2 and 3 dimensions. Really, he talked about that. He was kind of originator of calculus, but really the biggest thing he did was this idea of universal gravitation, right? Beyond that, we had this idea of the universal constant of the universe, or the gravitational constant of the universe, out of Newton's work, which is kind of really cool. I mean, really, he's the father of modern physics, right? In classic physics. I mean, from him, Einstein and other scientists took, their work. So if you don't know anything, if you don't remember anything from this class, I mean, a couple of things you need to know is you need to know Pythagoras, because we talked about him a little bit, because he affects games, because we use Pythagorean theorem for almost everything we do, Euclidean distance and all that stuff, right? And as well as Sir Isaac Newton, which he's like, one of the main guys who did everything that we do, who kind of talked about or researched, and through experimentation, really came about with some observations about how motion works. All right, so the stuff he really talked about is what happens when you push an object, where you throw an object beyond particle or projectile motion. He wanted to talk about how mass affects motion, and how that, he kind of developed this idea of energy, the idea of energies. Because back in the day, I mean, you got to think where this guy came from. It was kind of an abstract thought, right? Energy. How do I transfer energy? There was no, I mean, back then, even electricity was way off, right? It was magic, right? So, like you said, so you got to figure these guys say, okay, so imagine I want to understand the workings of the universe, how energy gets transferred. Why does a rock fall when you drop it? Like, why does it happen? Yeah, it's a lot of it was God. But now we know it's not just about God, right? For those people who believe, it's also about other things. It's about the idea that the larger an object is, mass-wise, it attracts other objects. So the greater the mass an object, like we're talking about in terms of planetary size, or at least a size of a large body, it exerts force, gravitational force, on other objects, right? And so start off with mass and energy, right? And you got to think about this before we move on from force. You got to think about mass and energy, how Einstein took this idea of mass and energy, and how he basically said that, hey, you know what? Energy, you can convert mass to energy, right? He made that famous equation, E equals mc squared, right? Where energy equals to mass times, the speed of light in a vacuum squared, right? That whole conversion from mass to energy, which gives rise to things like teleportation, right? I'm going to go there. I'm going to say it, right? Star Trek, transporters, right? All that stuff. That's where they got the ideas. They got the ideas for transferring mass to energy, transmitting it, receiving it, decoding it, and kind of integrating it, right? Now, we're way far away from that stuff because, and I think I've talked to some of you before about it, because if we want to make a transporter, a real-life teleporter, You got to scan somebody at the molecular level, or even deeper than that, right? At the quantum level, and not kill them somehow, right? So that's really weird. And we're not there yet. So there's still some technology that we're missing from figuring that stuff out. But really, it started with this idea of, hey, I want to transfer some energy. Well, where does energy come from? And the idea that energy can't be created or destroyed, right? Energy is always there. It's just part of the system. We're part of the system. There's energy around us, right? And we just got to harness that energy, magic, right? And use it. Actually, some of the best books and best, scientific theories all come from that. Where, hey, if I could harness the energy that exists in the system, the universe, right? And I can use it, it's much better than me trying to create energy, right? Which is not possible. So this is the, Newton's laws kind of give rise to that kind of stuff over time. There's different kinds of forces. There's contact forces. So when one object strikes another object, that's a contact force, like the football player kind of hitting a football. That's a contact force. There's pulling and pushing forces, right? Forces that we push and pull. Like I'm pulling something. There's friction. Field forces is interesting, where we have other kinds of forces that are around us. Gravitational forces, electromagnetic forces, strong and weak nuclear forces, right? All those kind of things that are involved in physics. To me, I have to talk about gravitational force. We're not going to talk about electromagnetic force in this course, nuclear forces or weak forces. We can't talk about those things. It's out of scope. And this is where, if you're ever interested in physics, which is a really interesting field of study, lots of applications for engineers and so on. The main things, that you can learn about is electromagnetic forces and nuclear forces and so on. A lot of work is still being done on gravitational forces. We still don't quite understand why. We don't have, I know they talked about it a few weeks ago, since we're talking physics, or maybe it was a month ago, about the idea of finding a graviton, right? It wasn't called a graviton, they called it gravitational particles, right? But there is no way of doing anti-gravity or anything like that, although it's, purely science fiction. We can almost imagine that this is possible, right? Because it's some kind of field, right? Field or particles that kind of are able to attract one to the other. When we find out, we crack the idea of gravitational force, what that is really about, I think we're going to be able to do great things like travel across the stars, right? But for now, our limited understanding is that big bodies of mass, like planets and stars and those kind of things, warp the space-time continuum. Truly, I'm not joking, right? And that warp, that almost like that gravity well that they create, pulls things towards them, right? And it's hard to imagine these things because our brains are not made to envision a gravity well in 3 dimensions. All right. So we're going to be talking about springs a little bit. Because again, we've got an adjusted schedule, right? And the ability that spring, we already talked about this kind of, where if you pull kind of a spring, it has this force, an elastic force that pushes it back into shape, right? Same thing if I push a spring. If I push a spring or if I pull a spring back to its elastic shape, the original shape that it had, right? Actually, if you think about it, all objects are really like that in some ways. Right? They always trying to find their original shape, whatever that original shape is. It's almost like an object in its material form has a way of being, and it always tries to find its way back to that original shape, one way or the other. And it struggles, it resists change, it resists changing shape. And that resistance can come into the form of friction. It can come into the form of all kinds of tension and tearing and all kinds of different kinds of forces, shearing forces, and all that kind of stuff that can stop an object from changing shape. And so, and a spring is a good example of that, where a spring, you pull a spring, it has this idea of a tension coefficient. We're going to talk about that. And as you push the spring, it has this other idea. And actually, when we talked Spider-Man in that last assignment, right? Spider-Man was one of your questions. One of the great things is that we kind of talked about this spring action already in the previous assignment, where you pull Spider-Man's head and he kind of bounces up, because what he's trying to do is, the web that he has is trying to keep its shape. is trying to go back to what it was. It has almost like a spring-like coefficient. We did it differently, but you can see how this works. So we use springs because if I put a weight at the end of a spring, and this is why it says if we calibrate, so we can use springs to calibrate force. So if I put a weight on the spring, right, and I let it pull down the spring, it'll really tell me how heavy it can be, this weight, how much mass, and there is a difference, by the way, between mass and weight. Does anyone know the difference between mass and weight? I think I covered that. Yeah.
Weight is the effect. Mass is how many molecules there are.
So mass kind of is akin to more density, more of a dense material. I can have a denser material that takes the exact same shape, and it'll have a greater weight, right? Whereas I can have the exact two materials, two boxes, let's say. They look like two cubes that are sitting there, right? And one may be way heavier than the other one because of the density, how many particles are packed into that same volume, right? So that's what mass talks about. So if I take two different masses, doesn't matter the shape, and I hang them on a spring, you can see that I'm going to have a vector that pulls the object towards the ground because gravity is pulling down. That's one of the forces that's pulling down on the weight, on the mass, right? Meanwhile, the spring is pulling back up. It's trying to, go back to its original shape. And it comes to a point where which we call equilibrium, right? It kind of forms that area where it's not going to continue to stretch because the spring can't stretch anymore, right? It's going to stretch as long as it can to accommodate that weight until it reaches equilibrium, right? Now, if it's too heavy, what's going to happen? Well, a spring could break. That's possible, right? Shearing forces could make the spring break. The top of the spring, the thing that's holding the spring to the ceiling in this particular case, that could break. That hook could come off, right? Or the bottom could come off too because it's so much force that the spring or the components of the spring can't support the object. All right, we can also have forces that are applied at an angle, right? We don't have to have up and down forces. We talked about gravity as kind of an up and down force, right? Or a vertical force, right? Actually, we talked about it when we talked about 2D motion and 1D motion. Gravity was a force in the y-axis in our case, right? Here, we can have forces that drag to the side. So perpendicular forces or horizontal forces, right? Where we have two forces, one that's pulling down, and that would be gravity, let's say, times, your mass, whatever it is, right? And then some force pulling across. Maybe there's something else that's pulling this spring in another direction. And then as you see, you have the resultant force here across this vector, right? So you have three vectors here. You have the vector that's F1 pulling down, a vector that's F2 pulling to the side with some particular angle, right? And then the resultant vector of where the force is really going, right, at the end of the day, right? That's really is. And we kind of talked about this, and that's why it's good to understand projectile motion and 2D motion, because this applies to what we're talking about here with, Newtonian physics. All right, so kind of a review.
Just one question, sorry.
Yeah.
So is the resultant force, is that the sum of perpendicular?
Yeah, so you had two forces, and what are you going to do? You're going to get x squared plus y squared equals z squared, and you're going to get that hypotenuse, right? So yeah, so to answer your question, absolutely. It's exactly what you thought, right? All right, so now let's do some at a very high level. Now the book says it quite a little bit differently, but let's talk about the first law. An object at rest will stay at rest. See, I was off for 6 weeks. I stayed at rest, right? I didn't move around. I got fatter and grew beard, right? An object at rest tends to stay at rest, right? An object in motion tends to stay in motion. Like those commercials, right? You're working out, you're going to keep working out. And it kind of makes sense because it's like it's not just a physical thing, but it could be a philosophical thing. But at the end of the day, that's what happens. And it says, the last part, it says, unless acted upon by an unbalanced force. So if somehow I have some force at rest, which means it's in equilibrium, right? So the pushing and pulling forces on it, whatever that object is, let's picture a cube sitting on a desk as an example, right? It's not going to move unless I apply some kind of forces to it, right? Now, what's going to stop it from moving? The friction of the table. Let's say if I slide a cube across the table, the force of gravity pulling it down towards the table, it's going to slow it down. All these things are being applied to the cube to slow it down that are unbalanced. Balanced forces mean forces in equilibrium, right? So an example, if I took a rock or whatever, I was in I have a spaceship, and instead of firing lasers or some kind of other kind of things, I use projectiles. I just pick up rocks from a moon and throw them from one spaceship to the other. Guess what? They're going to keep moving forever in space, right? Because in space, we have microgravity, and nothing's going to slow it. There is no unbalanced force that's going to slow that thing down until it hits something. So in some novels, science fiction novels, they have rock throwers, literally, right? Take some rocks from a moon, load it into a projectile cannon, fire it off at your enemy. It's going to be pretty effective. Imagine being hit by meteors, right? It's pretty crazy. Now, it takes a lot of energy to project those things, you know, and you can imagine the recoil that you're going to have in space. If you fire rocks in a certain direction, you're going to go the other way, right? That's a great way to escape, too. So you target your guns at some place, and your guns are actually your engines, and you just run away, right? So kill the other ship. So an object at rest will stay at rest. An object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. That's Newton's first law. Second law, which is key, which is where Einstein took the second law, and a lot of other physicists took the second law and made it into eventually E equals mc squared, which is force equals mass times acceleration. So if I want to figure out the force of a system or an object moving or whatever, I take the mass of the object and its acceleration, and I can figure out the force that's being applied to it. Okay? So F is equal to ma, key equation. If you guys don't know that by the end of this course, I failed, right? For sure. F equal to ma, right? M being mass, A is acceleration. So if I have a mass, let's say, for example, 10 kilograms, and it's falling, right? It's free falling. I take my mass times the force of gravity. That's the acceleration due to gravity, right? And I've got my force, whatever that force is. Now, if I'm suspending that mass, I'm preventing it from falling. If it's 10 kilograms, let's figure this out in our heads here, right? So force is always in newtons. Okay, when I say force, it's in newtons. Mass is in kilograms. Acceleration is in meters per second squared, right? So if I have a mass of 10 kilograms that I'm holding up, let's say I'm working out at the gym. I don't know why I would do that. Me being fat and have a beard, right? But let's say suppose that I just I don't know, I'm doing some kind of lateral raise at the gym with my shoulder. And I pull a mass of 10 kilograms. That's huge. I just leave it there, right? How much force is being exerted on that mass going down? Well, we take 10 kilograms, right? You multiply it by 9.8, right? So 10 times 9.8, so 98 newtons. That's how much force is being applied, right? To that weight that I'm holding up. And that's the way we figure out forces. Remember, force is energy. And if I have a certain amount of force, I have a unit, something I can talk about when it comes to force. Now, in games, how does this apply to games? Units, man, I got some energy. You got a variable called force, right? And now I have in a game, I have a number, 98. Let's say we wouldn't use 9.8 in a game, we'd use 10. Right? Because we're going to somehow round, unless you're doing some kind of physics simulation, chances are in a game, you're not going to use 9.8 meters per second, right? Unless you want to be deadly accurate, which is not going to happen. You're going to probably use 10 or some factor of 10, 10, 20, 30, especially if you're doing some kind of platformer where you want the motion to come up and come down really, really quickly. You're going to take that, multiply it by the mass, and you're going to have your energy, whatever that is. Once you have that energy, you can transfer that energy from one object to the other. And we're going to talk about that when it comes to momentum and the idea that we're going to be able to transfer energy from one system to another, right? And that's how collisions work, if you think about it, right? So here's a preview of collisions. I've got an object. It's moving in a certain direction, right? A car, right? With a certain mass, let's say 3,000 kilograms, right? And it's accelerating at 10 meters per second. I'm just making this up, right? So 3,000 kilograms, 10 meters per second, that's 30,000 newtons of force. That's coming at a wall at an angle of 30 degrees. What's going to happen? That car is going to bounce, baby. That's what's going to happen. It's going to also crunch up in the front because the wall is going to absorb some of that force. We're going to talk about this later, so don't worry if you don't understand everything. And the rest of that force is going to come back at the car, right? The rest of it, if you think about it, when it bounces off, it's going to try and the momentum of the system is going to try and continue. Most of it's going to be absorbed by the wall. Hopefully, the wall won't break, right? If it's a real retaining wall, the rest of it is going to be coming out in the opposite direction. And we're going to use dot product to figure that out, right? So for those people who forgot how to do dot product, cross product, all that lovely stuff, it's coming, right? By the end, next year in January, we're going to talk about it, right, in more detail. All right, so the third law, what is that? And this is an overview again. For every action, like I just talked about with the car and hitting a wall, there's an equal and opposite reaction. So what does that mean? So
the unbalanced forces thing comes in. If they
kind
are
of
balanced, they're equal and opposite.
well, okay. So think about this one. So you know, you're playing pool, right? This is a classic example. And when I shoot the pool ball, I hit the pool ball with my pool cue, right? It's going to go down a certain direction, right? The reason why it's moving is because I'm applying force to the pool ball from my pool cue, from my arm. That's where it's coming from. So my arm drives the pool cue towards the pool ball, right? Hits the pool ball at a specific angle. It's gonna accelerate at a specific rate. By the way, when you ever hit a ball with a pool cue, it comes back a little bit. The pool cue actually recoils. If you think about it, if you're actually really careful and watch it, that recoil from the pool ball to the pool cue is the reaction, right? Now the pool ball is speeding towards another ball. It hits another ball. Guess what? That ball, it transfers energy from the first ball to the second ball. But at the same time, because that ball has been is stable and in equilibrium, it's going to transfer energy back, right? So there's an equal and opposite reaction. Both balls will move. Notice if you hit a ball, the other ball kind of bounces in another direction, also comes backward, right? Because of the original ball, if they're the same mass. Now we're talking about objects having the same mass. If one object had greater mass than another one, then that would change the scenario. We're going to get into this more and more over the next little while, so please bear with me. Okay, so again, 3 laws of motion. I kind of outline them at a very high level. Physicists will cry today at the dining table, say, "What is he talking about?" Because that's how high level we're talking about right now, right? All right, Newton's first law. One of the things that we talked about when it comes to an object that stays at rest or in motion will stay in motion, object at rest will stay at rest. The idea of this frame of reference or inertial frame of reference, especially when it comes to motion, okay? What does this mean? It means that if I'm in motion already, right, the way I perceive the world or the way the object reacts to the world changes according to where you sit in the system. If I'm watching something happening, 2 cars colliding, I'm not in the car that's colliding, right? I have a different way. My frame of reference is outside of the system, right? When I'm inside the system, I feel the motion of the car, right? To some degree when it stops. But when I'm in the car moving, do I actually feel the energy that's being transmitted to move the car? I mean, I'm in the car. Do I feel it going 80 kilometers an hour or 100 kilometers an hour? No, right? If I put a marble on the top of my dashboard, as long as I'm going in a straight line and the road's not too bumpy, the marble's going to stay there until I stop, right? Then the energy is going to change. That's why we have seatbelts, right? Because, and especially fighter pilots are the people who notice this the most. Their frame of reference, they're traveling at a specific speed, right? But as soon as they accelerate, as they're accelerating, they're being pushed back into their seats, into their acceleration couches, let's say, that they're sitting in, right? They're sitting back and they're being pushed back, and then they slow down. They kind of slow down like this, right? And they're being strapped in because it's limiting the amount of motion. Because if they didn't have these straps, they'd fly all over the place inside their cockpit, right? Yeah, that too, right? So you're killing me, man. You're throwing me out. You're heckling me. That's terrible. But the idea is this same thing. If you're in motion, you're already in motion, you're driving on the highway, you don't notice how fast you're driving because your frame of reference, you're in the car, right? So too, when it comes to this law of inertia or inertial frame of reference, we talk about inertial frames to some degree, right? You don't feel it if you're inside the system. When you're outside the system, if we're outside the car, right? And I was riding on the hood or something like that, and the wind's blowing at me, now I'm outside the system. I can feel forces being applied to me because I'm not protected in the shell of the car. I'm outside of that frame of reference. If you've done that, then this is where you have this idea of, this feeling of forces that are being applied to us, okay? I know, guys, this is like some of you are dying. You're like, holy crap, he's talking philosophy. But this is what we have to talk about a little bit, right? I'm not going to talk about this too much, but think about this, right? Think about the Earth. We're on the Earth, and the Earth is traveling at a certain speed, okay? I think it's like something like 32,000 miles per hour, something crazy, that around the sun. Something really, really fast, right? So we're traveling around the sun. It takes us 365 days to travel to do that orbit, right? Okay. Meanwhile, the Earth is also spinning, right? So that we have a certain amount of spin in the Earth. So we cover the entire Earth whatever that thousands of kilometers are in a day, right? So we're also spinning that way too. Okay, at the same time, the whole system is spinning. The sun is actually on position in the Orion arm of the Milky Way galaxy. So that's the whole galaxy is spinning. So there's some inertial there happening, right? And then the whole galaxy is actually moving away from the where we kind of think about it's kind of expanding or moving away from itself, and also in a circular motion. So you can imagine that we're moving at, I don't know, something like hundreds of thousands of kilometers per hour, right? But yet we don't fly off the Earth and we don't feel it because we're in the system. Our frame of reference, we're in the system called, this Earth system where we're moving, and the motion, we can't feel the motion. We don't feel the acceleration of the Earth as it spirals around the sun and so on. So now, can you imagine a teleporter? Really, let's go back to that teleportation we talked about, right? I want to teleport to another part of the Earth, right? Instantaneously. Whoa, hold on. Every second, my Earth is spinning, right? Our Earth is spinning and moving around the sun, and the whole sun is moving, kind of thing inside the galaxy, and the galaxy is moving as well. My teleporter would have to adjust for all that stuff, right? Somehow. And there's all kinds of force that's being applied. So how am I going to zero out that force? That's a whole other thing. How can I zero out the momentum that I'm going to transfer, right? And actually, if you're a big, I don't know if you're a science fiction person, if anyone's a science fiction person in the room, hardcore science fiction, classic science fiction would be like someone like, I don't know, Larry Niven. He wrote some really great science fiction novels. And he talked about that in his matter transmission idea where, hey, guess what? The older matter transmitters in his world would transfer heat energy because, hey, as I'm transmitting, I'm moving from one place to the other. That energy's got to go somewhere. And it's in the form of heat in his novels, okay? So that's why, really, if you think about it, this idea of frame of reference, right? Although it doesn't appear to us in regular lives, we don't think about it, is huge when it and their idea of motion. All right. So there's an idea of an alternative statement, which is, I like this one, which is that which causes a change in the motion of an object. That's the alternative statement. So anything that causes a change in the motion of an object, that's kind of an alternative statement to his, an object at rest tends to stay at rest unless it's a some unbalanced force applied to it. Okay. So we have the idea of mass. Mass is hugely important with mass and inertia. The idea of inertia is kind of a property of an object that resists the change in velocity. Okay? Let's think about that for a second. So something that has a lot of inertia is something that I've applied a whole bunch of force. It's like I'm being resisted to move. Like a massive object has more inertia, right, than a smaller object because it'll resist the me trying to move it, right, a lot more than a smaller object, right? Smaller object, I can move it no problem, especially if it's smaller than me, less massive than me, I can probably move it. But if it's a massive object, like example, a building, that is huge amount of it'll take a huge amount of inertia to move that building. And when it gets moving, holy crap, that thing is, if I move a building like Superman, imagine, I pick it up and I'm throwing, nothing's going to stop that building from stopping, right? It's going to keep going. It's going to smash and destroy all kinds of things. Why? Because it's massive, it's huge, and it has a lot more inertia. Okay? So again, the way we think about mass is very important, especially with Newton's second law, where force equals mass times acceleration. Newton talks about mass all the time. Okay? Mass, again, is a scalar. It's not a vector, right? So that's why we can multiply it versus, we multiply it with acceleration. Mass times acceleration, scalar times a vector. Acceleration is always a vector, right? We think about the force of gravity as the most common acceleration because we know about it, right? And the force of gravity is a vector pointing down towards the Earth, right? In the game, from a game sense perspective, depending on your frame, depending on how your coordinate system works, like for example, SFML. Who knows SFML really well? Anybody? Okay. So where's your 0, 0 point in SFML? Right? Your origin. Top left, right? Okay, what about in Unity? Where's your we saw that when we left, before we left. Where's that 0, 0 point in Unity units? Somewhere in the middle, right? Which is kind of weird, right? So if we're moving up, right, in Unity units, we're actually physically moving up. It's a positive motion. Down is negative, right? Whereas in SFML, if we're using those units, that coordinate space, right, moving down is positive, right, because we're growing to the right and we're growing down. When I say grow, I mean like grow. That's how the computer is rendering the frame, right? It's kind of drawing it to the right and down. So that's why gravity is a vector, depending on the frame of reference. Going back to reference frame, it'll be different. And mass is a scalar. Okay, so if you multiply a scalar by a vector, right? What do I get in the end? Does anyone know? If I take a vector and multiply by a scalar, what do I get? What's the result? Vector, right? Because it's like if I take, who knows GLM, that whole library, GLM. You guys have been studying that a little bit, no? You guys never heard of the GLM library? Oh, it's the graphic library for mathematics graphic library, right? Well, if I make a vector 3 out of a three-dimensional vector, you know, in any math library, even in Unity, and I multiply it by something, and a scalar, some value, a variable, I'm going to get a vector at the end. Think about this. Okay, we talked about mass versus weight. So this is interesting. If I have a greater force of gravity, notice how I said that, a greater force of gravity on the moon, right? So, or if I had that, then the same amount of weight would be it'd be heavier. It would appear heavier on the moon, right? If we had a greater force of gravity. But of course, it's actually the opposite. The moon has 1/6 Earth's gravity, which means anything that's on Earth would be a lot lighter, or appear to be in that current reference frame. In the reference frame of the moon, it would appear to be lighter, right? It wouldn't be any less massive, however. It would have the exact same mass. The same molecules would made up that object. That volume with the exact same volume of material, but it would appear to be lighter. Why? Because the force of gravity would be less. If we think about if we're thinking about the force of gravity on Earth has 10 meters per second to round it off, and we say it's worth 1/6 of that, we would take 10 times 1/6, so divided by 6. What is that? Can anyone tell me that really quickly? Take 10 divided by 6. Just give me a rough estimate. Anybody?
1.7.
Is it 1.7?
I'm pretty sure. 10 divided by 3 is
1.6? So let's say it's 1.6. So instead of like 10 meters per second, it's 1.6 meters per second. Take 1.6, multiply it by 10 kilogram mass, right? Instead of getting 98 or 100 newtons, it would be only 16 newtons. So a lot less force, energy, would be actively being applied due to the force of gravity on an object on the moon than it would be on Earth. But the weights would appear to be different. And that's the difference between mass and weight. All right, so here's an overview of the second law. So we really talked about the first law, mostly to deal with mass and an object at rest in a state at rest. I was also looking at the time here. We've been going for about 30 minutes. And I'll probably go for a few more minutes and take a short break because some of you are dying, right? You guys aren't used to being in school. Not my fault, but I feel bad, right? So the net force of an object, like it says here, is equal to the product of its mass and acceleration. And like we talked about, F is equal to ma, and I want you guys to remember that. If I ask you to remember anything, and probably I won't, because I'm probably going to get you guys to make a sheet, or I'll give you a sheet. You can modify again for your next test, and I will allow you to modify your sheet next time. Add whatever you want on it. Anything that'll fit, probably handwritten, right? I don't know. Maybe I'll let you guys do your own digital thing. Who cares? Then you'll have this formula, and then you can add your own formulas. Okay, that's all I'm going to say. And you can add your own test cases or example problems or whatever. Now they go into quite a bit of detail here in the book where they talk about. Now notice this is when we look at some of these things. When you see this notation, again, this is an alternate notation that we've noticed. What does this sigma stand for? Anybody remember from math? Sum, right? If whenever you see a sigma in a formula, how do I convert that into programming? What do I do with sum? If I have a sum, if any time you see sum in a formula, what would I do? What's that? It's a for loop, right? Anytime I see a sum, if you see a sum in a formula, whenever you look at a book, you're like, okay, so the sum of all forces, as an example, That means that I want to add up all the forces. That means I got to be able to take a force and keep adding it from, let's say, from I to N, right? Where N is equal to the maximum amount of force, right? I'm looking at a for loop or some kind of looping structure anyway, at any point. But here what they're talking about is the sum of all forces on the X, Y, or Z planes, right? Kind of, you know, you can kind of derive those by taking the mass and multiplying it by the acceleration across different axes, right? So we're not just talking about two-dimensional motion anymore. We're talking about motion in any direction, right? And when we think about this, we add up all those forces, whatever they are, and we have a net force. Net forces. So imagine if you're programming a video game, and I want to talk about things like wind now. If it's, let's say, let's look at a 2D video game for a second. So 2D, I've got some wind going across the screen. I'm shooting a cannon, so I've got that force. I got to think about that force across the x-axis. Maybe I'll have gravity across the y-axis. Probably in a 2D game, I don't want to think about the z-axis. So let's just look at those two forces. And then maybe there's other forces as well, not just the wind resistance, but other forces that we can come into play. Maybe I'm shooting a projectile with a particular acceleration, like some kind of missile, as opposed to a bullet, right? And the missile can direct itself in a certain direction. That's another force. And we can kind of combine all these forces until we have a sum of forces across different axes to get my net force, which would be a vector in a particular direction. So take all the forces, add them together, use Euclidean geometry, or the stuff we talked about in the first day of class, right? We're going to use trigonometry to figure out where the net force is going to be. And that's why I wanted to talk about trigonometry day one or week one with you guys, because we need them. We need it now when it comes to physics, and we needed it before we went on the break. Okay, so that's really Newton's second law in a nutshell, where it really discusses or kind of goes over, or it's F is equal to ma. And again, the units are newtons and typically kilograms, all right? You could also use pounds. I'm probably going to not make you convert. I'm probably going to use mostly kilograms in my examples. Okay. We talked about gravitational force at length, but I want to start calling it gravitational force, or the force due to gravity, as opposed to just gravity, all right? Because I want you to always think about gravitational force as energy, right? That it takes energy for that gravity to be in effect, right? It's almost like we have this gravitational field that's inherent in most large masses, right? If you think about it that way. And there's some kind of energy that's being applied to you at a constant amount, constant rate, right? And it's not going away anytime soon. Some people think it's because of most planets have some kind of dense core. That's the reason why most of gravity works. We don't know 100%. Okay, I'm not going to talk too much more about weight, okay, because we've talked about weight at length. I'm going to go into the third law just really briefly here. And let's think about what this object, you know, whenever you apply an object or force to an object, you get an equal and opposite reaction. Well, think about how a bird flies. That's why I have this picture here, right? Where, you know, the wings beat down on the air, and what happens is the bird goes up, but at the same time, as the wings raise up, it goes down, and it keeps. If you notice, the bird doesn't just sit there in flight. The body of the bird keeps kind of going up and down a little bit, up and down, up and down, up and down, because the wings keep beating as it continues, right? And the wings aren't just going up and down like you know, some kind of you know, an object just goes up and down. They're also formed so that they're kind of moving backwards, almost like the bird is pushing against the air to fly. Just like the way we swim in water. When we swim in water, we push against the water, back against the water to propel ourselves forward. Yeah.
Doesn't that like change your center of gravity as well, though?
It does. Yeah, it does. So but what happens is you're slightly.
Yeah, I wasn't sure about forward and backward.
Oh yeah, it does, but slightly. But your center of gravity is usually. I want you to think about it for our example, center of mass. Okay, so whenever you think about an object, let's say anyone do any kind of 3D work at all, like Blender, Maya, anything, 3D Studio Max. Well, whenever you have an object in some kind of 3D system like that, you have almost like a center of that object. Almost like your pivot point, if you will, right? Well, I want you, when we're in this course, because it's a game course, I want you to always think about the center of mass as the area that's being acted upon, right? So if I have a large, weird shaped object, we're going to figure out that center of mass somehow, and that's what's being worked upon. For irregular sized objects, which are outside of the scope of this course, right? You would try and figure out the center of mass based on all the mass, the way the shape of the object, the volume of the object. For us, what I would do is probably cut that object down in a bunch of different objects, smaller objects, to figure out where the approximate center of mass is.
But by default, unit is the element contains the entire weight, right? It's not like a frying pan where the pans have the handle light.
Yeah, or though, but you could break down the object into different objects.
But by default,
yeah,
this thing is one unit.
yes,
Yes.
yeah. So by default, you're right. So if you have a game object in Unity, then it's one object typically, right? However, I want you also to think about the game object like us. If you could think about a human being as a game object,
Yeah, if I take my hat off, it's one pound.
right? So the system that is you, right? You have clothes on, you have other stuff, you have fluids inside of your body. You know, I'm not going to go there, Corey, but you know, other things. Who knows? Maybe smoke in your lungs, right? I don't know. But at the end of the day, right? All these things make up the game object that is core, right? Or the container that is core, right? And your center of mass somewhere in the middle of your body, right? And that's what we use to calculate our units and everything else we're working with in this course, right? So again, one thing I like about, I'm just going to move on to some of the stuff we haven't talked about yet, is this. So let's say, for example, you might see some notation where I have a force. Remember, Newton's second law is all around force equals to mass times acceleration, right? I said that a bunch of times. So I have two objects, object one, the blue object, object two, kind of the golden object or the golden yellow object, I don't know, the brown object. You can think of it different ways. Hey, I only see in 13 or 16 colors. So I was going to say 13 colors for some reason. I don't know why. But I'm missing a bunch of color ranges, right? But anyways, either way, it looks gold to me, right? So when you look at this object, object number two, notice that the force says F12. And the reason for it is it's the force going to object one from object two. That's why I want you to think about it, this notation. And the same thing goes with force F21. It's not force 21. It's the force that's going from or to object two from object one. That's how what this notation really means. And notice that you have this other equation that says, well, the force 1, 2 is equal to a negative force of 2, 1. Why would that be? Because at the end of the day, when those two forces hit, you're going to get some kind of motion in either one direction or the other, right? Why is that? You're going to get, imagine two things coming at each other. If both things are the exact same mass, they're just going to bounce back, right, with the resultant forces. So if I apply a force of 10 newtons, let's say, on each force, forget the mass, right? But let's suppose that the masses are equal, whatever the masses are. They're mass of 1. 10 newtons come at two objects that have of 10 newtons of force hit each other with equal masses. They're just going to bounce back with 10 newtons of force in the other direction, right? Now they're going to stop because of gravity, of friction, all those kind of things are going to stop them. They're not going to keep going forever unless they're in a vacuum, which means space, right? That's the only thing that's going to stop them is friction and gravity and all that stuff. Now, if they're perfectly circular too, if they're not perfectly circular, that also creates another obstacle, right? So I'm just showing you this example so you can see that this action-reaction example is all around energy being transferred from one object to the other. All right, here's another one. We have a computer monitor on a desk, okay? What forces do we have? Well, we have the force of gravity applied to the computer monitor, right? Force of gravity. But we also have something called the normal force, right? That's pushing up from the desk, okay? There's a normal force, N, that's pushing against gravity. Okay, if the computer is resting on the desk and is not moving, we can say that it's in equilibrium, right? It's not moving. So therefore, we can assume that the force of gravity is equal to the normal force, all right? The normal force that's being applied up, right? At the same time that gravity is being applied down. They're equal. It's in equilibrium, okay? And this is a really key concept because notice that the same amount of energy is being used to keep an object on a surface as it is pulling it down. Now, if let's suppose that this object was massive, right? Like I'm talking about, as it was not just big, but really dense, right? Then obviously it would be torn through the desk, right? Because the desk, the normal force would not be able to support the mass of the object, right? Because the materials of the desk aren't able to support that, as an example.
Is the normal force something you calculate then based on the object resting on its mass?
Typically, when we use it in a problem example, we'd say this. If it's resting on the ground, an object is resting on the ground, then the normal force is equal to the force of gravity. Okay?
I'm saying if it's on an object, that's something more
If it's on another object, right, then we have to make sure that the force of gravity isn't going to tear it through that object. For example, if it was some kind of object that was really light or not very dense, I don't know, for example, a piece of paper. You had a really heavy weight, can you imagine a 10 kilogram weight on a piece of paper? It's going to tear right through. So the normal force wouldn't be enough to support the gravitational force coming down. Okay? In this case, if you're given an example like this, you know that the normal force is bolstering or maintaining the equilibrium of the system. Therefore, it must equal to gravity, right, in this particular case. And on that, when we start thinking about these things, notice that we have this idea of a free body diagram, okay? So I have these two forces, the force that's acting down upon an object and the force that's repelling, gravity or pushing up on the object. Yeah.
Free body just means it's not like attached. It's not sitting on the desk. It's hovering from a string or something like that.
Well,
right?
it's just a way of us picturing it. So imagine if it was in space, right? We have an object in space, right? It's easier for us to imagine a free body diagram by taking a look at it's a model for us to understand what's happening in the system, right? So here's an example of a free body diagram, right? We have the force of gravity and the normal force. We don't have an object. We don't have a diagram of the desk or the monitor. And we use the dot, that dot in the middle, that circle in the middle, to kind of say that's the center of mass. So we always put the circle at the center of mass. So if I get you guys to draw, which I may do that on your assignment, a free body diagram of a system, then what you're going to do is you're going to take a look at the system, what forces are going to be applied to it. You're going to draw arrows down and up, right? And in this particular case, it's pretty simple because there's no angle. The desk is flat, and you have an object on the desk, and it's being pulled down by gravity, and it's being pushed up by the normal force, okay? So it's pretty simple. This is the free body diagram of what we just talked about, okay? Any questions around this? Because I know sometimes it's just an abstract way of us breaking down a problem and understanding the forces that are being applied. So I'm taking the sum of these two forces on the y-axis here, right? And they're equaling to 0. If I take the normal force and add it to the force of gravity, I'm going to get 0 at the end of the game. The sum forces in the y direction in this particular example are 0, right? We don't have any sum force in either direction. If I had a force going downwards, that means I would break through the desk, right? The normal force wouldn't be enough or whatever. That desk wouldn't be able to support my monitor or whatever.
Do you always consider the normal as, say, if it was an inclined plane?
We're going to talk about that. Yeah. But you would have a normal to the inclined plane. So the inclined plane you'd have the normal going, the normal, like we do in GAME, to the inclined plane, the perpendicular to the inclined plane, 90 degrees. And whenever we think about a normal, I want you to think about that. Think about it 90 degrees to the plane. All right, whatever that is, to figure out the normal. All right. We talked about free body diagrams, helps us isolate the problem. We make some assumptions. We want to think about all objects as particles. We always want to look at them as, even though they're massive objects, we want to look at the center of mass. We talked about that. These are the assumptions we're talking about. Okay? So I'm going to skip forward, and then we're going to take a short break because we've been going for a while. All right, so here's an example of another object in equilibrium. In this particular case, it's not the normal force that I have, but the force of tension, right? The tensile force, right? I've got an object here hanging from the ceiling. It's a lamp. It has some kind of mass, right? The mass is being pulled down by the force of gravity and being bolstered up from the tensile strength of the chain that's holding it to the ceiling, okay? In this particular case, we can say that the lamp is in equilibrium because it's not falling, okay? And it's actually being, kind of suspended from the ceiling, and it's stable. It's not moving. So in this particular case, we have both objects. So why would we say, when we talk about equilibrium, how does that have to do with Newton's forces or Newton's laws? Well, it's an opposite and equal reaction. We have this reactionary force because we have a tensile strength to the chain, and we have this force of gravity pulling in the other direction. The resultant force is 0. Okay, and this is key. Whenever you see something hanging or on a spring or something like that, you know at the end of the day, if it's hanging in equilibrium, if the question says an object is hanging in equilibrium, whatever, you know that the total sum forces going up and down are 0, right? That means the only thing you have to think about sometimes is the force going left and right. For example, a pendulum, all right? If I have a pendulum, people who don't know what a pendulum is, imagine if I have a cord, and on the cord I have a mass, and I'm just rocking it back and forth, right? Back and forth across, let's say, the ceiling, right? If I do that, you know that the up and down force, that y force, is 0. And the only forces that you're getting is the x and y, the x force across this way. The horizontal force is what's making the pendulum go like this, kind of, if you think about it. All right. So whenever you look at this thing, we want to draw a free body diagram to understand what's happening here, right? And so what we do is we take the free body diagram and we apply it to the system. Here's another example. I have a crate, okay? And a man is pulling a crate across the floor, okay? What forces are being applied? I know that I have the force of gravity pulling down on the crate, right? I have that. I know that I also have the normal force pushing up on the crate from the floor, right? I also know that there's a force that's being pulled by the man. He's pulling this crate along with him in, let's say, the x direction. Now, in this particular case, it doesn't mention any friction. So we can assume that the ground is frictionless. You're on ice, right? Let's just suppose. So that if the man's on ice, this would be the case. We could draw the free body diagram. An arrow going down, an arrow going up, and an arrow going towards the direction of the man is pulling, right? Free body diagram. But there's no friction. If there was friction, we'd have another arrow going the other way in the opposite direction of the man that the man is pulling. We would take the resultant forces, add them up, and we have a resultant vector, the direction of this object, if it's moving anywhere, right? I want to stop here. I want to, before I go on, let's take a short break, and when we come back, have a little bit of a smoke break, bathroom break, whatever. We'll come back. We'll finish up as much as we can.